Hi everyone, this is a continuation of the previous video on Hess's law. If you haven't watched that video or if you're shaky on Hess's law, it would be best if you went back one in the order and watched that one first. In this one, I'm going to focus, we're going to do a practice problem, but I'm really going to focus on explaining the diagrams that I like to see people draw with these, that I generally refer to as enthalpy diagrams. And really all it is kind of a map of the enthalpies of the process, and it's kind of a graphical way of representing Hess's law. So this is the answer here to the question that we did in the previous video. So again, if you haven't watched that, go back and watch it. But anyway, so we're starting from there. So we've already solved this problem. We had these reactions that we were given. We found the delta H of a reaction we didn't know the delta H for. And now as a follow-up, we're being asked to draw an enthalpy diagram for this process. The basic idea is that you're going to draw enthalpy, that's a terrible y-axis. You're going to draw enthalpy as as though it is a y-axis, but there's no x-axis here. So up and down is the only thing that matters, all right? So we're going to have some starting place, and it really doesn't matter where, all right? But I can see we're going to have to start. Usually I say somewhere in the middle, but we're going to start a little lower than the middle because we're going to run out of room. So this first reaction here, we have to go up 2,250 kilojoules per mole. I'm going to way run out of room. So, okay. Oops. Okay, let's try this again. So we're going to start down here. And we're going to go up 2,250. And then for this process, so that is the amount of energy that would be absorbed going from these reactants to these products. And sometimes it's handy to label the lines with these, and sometimes it's really distracting. So I'm going to go ahead and do it here because people always ask about what's on the lines, and what's on the lines, again, is not as important as the arrows. This arrow here that we've drawn is going up because the delta H that we're working with is positive, all right? So now this second reaction is going to go up not quite as much as that last one because it's not quite as big. It's still pretty big. That's a positive 1940 kilojoules per mole. All right. And then when we get to this line, what we've created is 2 moles of H2S, right? And really, I should have written that on the other side because I'm going to need to do the completion, I'm going to need to finish this up. So we're going to go down from there, and I'm just going to extend this line over because I need to not draw things on top of each other. We're going to go back down minus 255 because that's my third reaction. Now overall, how far have we gone? Well, we've gone up overall, right? Because we started at this line down here. This is where we started, right? This is where we finished, right? So overall, we've gone up. And how much have we gone up? Well, we've already calculated that, right? We've gone up positive 3935 kilojoules per mole. Okay? So, and again, I'm going to erase the reactants and products here because they're really distracting. So we can just focus in on the energy diagram, right? This is just saying that the first reaction went up in enthalpy 2250. The second reaction went up another 1940. The third one went down 244. Overall, we've gone up 3935. The analogy I like to give for this is that think of this like a building, right? So, and the building has 2 elevators. And let's say you went up, well, it'd be ridiculous to go up 2250 floors. Let's say you went up 22 floors and then you switched to the other elevator and you went up another 19 floors and then you came down 3 floors. I don't know. Anyway, if you go up one elevator, get out, go up again and come back down, how much have you gone up overall? Well, this diagram helps you figure out, helps you see that. You've already done the math up here, right? You've already done this solution. And the diagram is just there to help you see it, okay? So, so the overall delta H here, right? This is the overall delta H for this process is just the total of how much you've gone up and down, right? So, so yeah, again, if you want to label the lines, you're certainly welcome to. It is not as important as labeling, as understanding what's going on in terms of the energies, okay? So what I'm going to have you do is I've got a whole new Hess's law problem, and I hope this one works out. I spent a lot of time trying to come up with a new problem, and it's a pain, it turns out. So I hate doing these from scratch. But anyway, so pause the video, get a pencil, get a calculator, try to do the problem, and then hit play, and we will go over the solution. Okay, so hopefully you have at least the start of an answer here. So we are trying to get to this reaction right here, right? That's what we want to get these down here. The given reactions, we want them to look like that one. So I notice that first off, that CO2 only appears in this first reaction. Water's all over the place, but CO2 is in this first reaction. It's on the wrong side, and it needs to have a 2 in front of it. So we're going to flip that around. We're going to make that 2 CO2 gas plus 4 water gas yields 2 CH4 gas plus 4 O2 gas. So we've flipped the sign of delta H and we've doubled it. So this is going to be positive 1606 kilojoules per mole. So far, so good. We've got ethanol in this next one, and it's on the correct side. So it looks like we don't have to do anything to that one at all. So we're going to do this as 2 CH4 gas. We're just going to copy it down, in other words, plus O2 yields ethanol, C2H5OH, plus water, gas again, and the delta H just stays the same, minus 381. All right. Now, notice that in this one that we're trying to get to, we need liquid waters, and everything we've got is gaseous water. And so we need to get some liquid water on the reactant side, right? And so we're going to multiply this whole thing here through by 3 and flip it because the liquid's on the wrong side. So we got 3 H2O liquid yields 3 H2O gas. So now that delta H is, I should be able to do that in my head, 132, I hope, and that's now negative, right? Yeah. Okay, so now, now we got to make sure our reactions add up, and then if they do, we can add the delta H's. So we've got 1 oxygen here, we've got 4 over here, so that leaves 3 over here. That looks good. We have the waters are kind of fun. So we've got 3 gaseous waters and a 4th gaseous water, and we've got 4 gaseous waters here. So we're going to drop those out. Yay! And then what else? CH4. CH4 is going to drop out as well. And again, if you're fuzzy on the dropping out part, it's just you're creating it and then using it up immediately. So some people like to refer to that as canceling in analogy with the algebraic process, and that's totally fine. I think that's fine. So what do we got? We got 2 CO2s left here. We got 3 waters in the liquid form even. And then what do we have over here? We have an ethanol that we haven't canceled out. And we have 3 oxygens. All right, so we're in business. Now that means we can add the delta H's. So we're going to do 1606 minus 381 minus 132. That's going to give us 1093. I hope. If I'm wrong on that answer, please let me know. And that's a positive number, okay? So now when we go to draw our enthalpy diagram here for this, how are we going to do it? Okay, so let's just scroll down to here, all right? So we've got, we're just going to start somewhere in the middle. So I'm going to draw an arrow here. And again, Y is enthalpy, so up is positive, down is negative. So we're just going to start somewhere. We're going to go up, and that's going to be up by 1606. And I'm not, you shouldn't be too concerned about, what am I doing? You shouldn't be too concerned about, the bigger the value of delta H, the longer the arrow needs to be. That part you need to be worried about. I'm not worried about you doing it quantitatively or doing it on graph paper, even though I have graphing squares available to me right here. You usually won't on an exam, so I'm not going to be too worried about it. Okay, so that's our first step. So you've gone up the elevator 1606. You're going to come down the elevator by 381. Get off, switch elevators, come down another 132. All right, so you started here. You're going to end here. So overall, you could have shortcutted all of this process instead of taking 3 different elevators, but you didn't. So, but if you had, you would have only gone up by 1093. And I've done a really bad job of drawing this here. This is not at all to scale. But the idea is still right, and we're going to run with it. Okay, so the biggest thing here is that if it's a positive delta H, the arrow goes up. Okay, if it's a negative delta H, the arrows go down. Okay, and then it's important to connect your starting point to your end point, and that's going to show the overall delta H, which is what you were finding in the Hess's law process. Again, this is all just to emphasize that enthalpy is a state function. It doesn't matter how you get there. It doesn't depend on how you get there. Any way you go is going to have the same total overall change. All right, and so because of that, we can do this process and we can use it to find the delta H's of unknown reactions. All right. Okay. I hope this was helpful. If not, or if it was, feel free to leave a comment and get in touch. And thanks for watching.